So last time we were in the process of doing our first of two remove methods, and we kind of ended early. So let's kind of ground ourselves back in what we were doing with remove. So this remove is going to be passed an index. We want to remove whatever node is at that index. So if we pass 0, we want to remove the head. If we pass 1, we want to remove heads.next. If we pass in 100, we're gonna have to do some iteration to figure out what the 100th element of the linked list is. I guess technically the 101st element of the linked list, and go delete that. So we have a couple of different error checks here. We're checking for index out of bounds exceptions. One, if it's less than 0 or greater than size, both of which are out of bounds. The other would be if we're looking for the list being empty. If the list is empty, then we can't remove anything from it. If index is 0, we have some special case, we want to remove the head. So to do this, we need to actually reset the head. So we store off our data as the heads data, the node that's going to be deleted. Then we say that the new head is the current heads next, which just says now whenever we point to the start of the list, we're going to be pointing to the element that is after it. We talked last time about the Java garbage collector coming and cleaning up that memory so that we don't have to worry about that. In other languages, you do have to manually manage your memories. You would have to, the reason I bring this up is if you're programming in C++, for instance, C, then you actually have to allocate and deallocate your memory. So this becomes something that you need to think about if you're using that kind of language. Whenever you fail to have a reference to something, before you do that, you need to free that memory before you lose access to it. As soon as you've lost access to it, it becomes ghost memory. It's like there's a student who's in the class, but they're not in the class. They've gone away. I have no way to refer to them. They're invisible and they're not there. So I have no way of communicating with you anymore because I don't know where you are. You're there, but I can't access you in any capacity. So not a huge concern in Java, but it's worthwhile. I try to teach as many of these courses as I can language agnostic because I don't know what languages you're going to be using in future classes, in future jobs that you're going to have. So I want to make sure that we're talking about some of the things that are not just Java specific. Questions before we dive into more code? All right, so we're in this else clause. So this means that we're going to be removing something that is not the head. So to do this, we need to go figure out which node that is going to be. We call this node retrieve. We're going to access the node before that. So we want to find the node before the index that we want to remove. This is going to just iterate as far up as I is, and it's going to find the node that is before that. So if we pass in index 1, find node before should go find the head. If we pass an index 2, then find node before should go find heads.next. We pass an index 3, it'll be heads.next.next. So it will just iterate as we did when we wrote the find nodes before. Just to point out for the sake, remember that this is a private method that we wrote. There it is, which means that it can only be called as a helper method from our own code. The user can't call this, so it's just something that we can use to make our lives easier because we have now multiple places where we call this logic. We call this general concept decomposition. Whenever we find that we're going to be repeating code, copying and pasting code, we want to factor that out into its own method. So this is a perfect example of this because we called it both in add now and in remove. Find node before is called here on line 73 and here on line 88. So since it's exactly the same logic, we don't want to copy and paste it. If you find yourself wanting to copy and paste code like this, that means that it's time to factor it out into its own method that will make your code shorter. And it also means that you can name that section of logic. This find node before makes this code significantly more readable, right? When you look at this first line of this else, it actually intuitively, logically in English kind of makes sense without, even if you didn't have the perspective of the rest of this code, if you knew in general what a linked list was, the fact that we called this node prev, and then we're calling some set of logic called find node before, it's not just this big logic dump of code, it's something that has a name associated with it and increases the readability of our code. All right, so we stored off the data, we grab prev, which is the node before we want to delete, and we were going to return here this element of the node that we're trying to remove. So we need to store that off. We're going to call this data. We're going to go grab it. Prev.next gives us the node that we want to remove. .data gives us the data of that associated node. So this just tells us we're going to store off the data from the node that we're planning to remove. I think now we're ready to start making some changes. So what do we need to do to actually go delete this node? Now that we've stored off and are ready to return that information once we successfully remove the node from the list.
Do prev.next, prev.next. Skip over that.
Yeah, so we absolutely want to do that. Are there any special cases that we would need to make sure of? Do we know that prevs.next.next exists? We don't. If we're trying to remove the tail, then if we try to dereference that .next and it doesn't exist, we will get a null pointer exception. So this is an excellent idea. That is the default case, but there is a side case that we need to consider before we decide to do that. So we're going to say if we're removing the tail, so in our code, how are we going to specify if we are at the tail? What logic could we put inside of this if statement to say that? Yeah, we want to call the size function. That's exactly right. So we want to say if the index that they pass in is equal to the size that we haven't implemented yet, but it will be trivial to implement when we get there, -1, then we are trying to remove the tail. It's not size because the list is 0 indexed, so we have to subtract 1 from the size to make sure that we're accurately removing or identifying the tail here. When we do this, then we want to say that what? How do we state, or what's the logic associated with that we want to do to correctly tie this in? So maybe I can draw this up more. It'll make it a little bit more sense. So here we have the node prev. Here we have the node that I'm just going to call index, since it's at index, and this is at index -1. And then this points off to nothing. I guess I've technically in the past done this. So we have some value, this points here. There are some values at prev and index that don't matter, but this points off to nothing. So logically, what do we want to do?
Prev's next to null.
Yeah, we want to take this arrow to delete index. We want to change this arrow from pointing here to pointing at nothing. So it really is also just null. So you don't even necessarily have to think of it as going to the same X. You could just turn this into that. And that would also represent the null. And now there's no reference to this node, so the Java garbage collector will come and this one steal my eraser that I brought in here. That's mean. That's really mean. Oh, it's over there. It's always as far as possible from wherever I. Thank you. I'm known to not have eyes, as well as having the memory of a goldfish. So now that there's a garbage collector, they'll see that there's no reference to this node, and now it will go delete it. And something is going to be pointing at this prev. There's some prev -1 index here that's pointing at this. So the garbage collector will not come delete the prev node, but that will get rid of the node that we want to get rid of. So logically, we just want to now take that idea and turn that into code, which says prevs.next is null. That'll get it done. When we do this, we successfully deleted a node, so we need to bump down the size. And return, since we're trying to return something of type T, we want to return data. Remember when we added, we were just worried about were we successful or not? So we were returning true or false. Now, when we're successful, we want to return the element that we stored from the node. So we want to return data. This should work for this. Now we can go to that default case. If we're not removing the tail, then the node at position index is actually going to have a next. So now we're not worried about dereferencing null. So we can do the default case. So we want to say that prev.next is the exact same left-hand side of the expression, but now what is the right-hand side of this assignment? Prev.next.next. We want to take the prev.next is the node that we're trying to remove. .next brings us past that. So in this case, we have prev pointing at this node that we want to delete. And we have some node that's after that. So we want to take this reference that's referencing our index, and we want to redirect that to this. So to change this to this, we take prevs.next. This is what we want to set, and we want to set it to prevs.next.next, which will point us at this node over here. So this gets rid of this arrow, and now we see for the Java garbage collector that there's no reference to index. So the garbage collector will come keep this node and free the associated memory. And now we see that in the list, now the next actually points to what we intended after we deleted the node. Questions about that logic? Yeah. So I guess we technically, how would we embed it in this logic? I guess would be the question. So we have kind of a one or the other that we want here. We need to check and make sure that it's null. If it's not null, we want to do this. If we try to say prev.next.next and this node doesn't exist, so let's again draw this back the way that it was to further motivate why this is. If this is the tail of the list, so this leads to nothing. If we try to say prev.next.next, that is a node, that would be null, wouldn't it? Yeah, so I guess we could technically do that. And it would be null here. So no, you are right, we could combine these. I'm always hesitant to do things like that, but you're absolutely right that it would work in this case. We know that prev.next exists. Yes, because we counted it in here. I think that will work. If it doesn't work, we'll figure it out. Anyone see an issue with doing this? We buy that it's going to work. If prevs.next.next is a node, so prevs.next.next can be null. But the .next is a node reference. So that's allowed to be null. If we were trying to dereference this with something like .data at the end of this, then that would be an issue. And obviously now we have a type conversion issue. If we're trying to store off some element, like a T element equals something, then prevs.next.next.data, now we'd be dereferencing null. That is a great point. But since this is a .next, when the type of this is a node is allowed to be null, and we can set something to be null without dereferencing. So dereferencing it is when you're trying to access one of the fields of a null object. That's when you get the null pointer exception. So I think this is going to work. And if it doesn't, we'll get some error at some point and know to go debug it and fix it. All right, do we buy that this is complete and correct? Anything else that I need to do? All right, I think we'll move on then to our second remove function. So if we go back to our interface, our other remove says that we want to grab an associated element and remove the first time that we see that element in our linked list. Before we get started with this, let's think about the logic of how this is going to work. Someone walk me through the English logic of what we want this remove to do. Well, again, exactly these same.
Removes all instances.
I think it's supposed, is it, do we want all or do we want just the first?
Don't we already kind of do just the first in the other one?
Remove gives an index. We say remove what's at position 4. We have no idea what's at position 4. This would say, if this is a linked list of integers, it would say remove the first node that has data 5, or that has data -12, whatever the query is. What we're passing in now is one of these generic elements. So if T is instantiated to be an integer, then this would be an integer. If it's a string, then the element would be an associated string. If it's a person object, then we would pass in a person object, and it would look for equivalence between the object that is passed in and the object that is stored in the linked list. So now we're looking for the actual data that's in the linked list nodes.
Can you use different exceptions than what's in the interface? Because it's like on that one, it says we have the illegal access exception.
Yeah. Yeah, so no, this isn't quite right yet, because there's also no index. So we need to figure out exactly how, so is empty, this should be an. It's empty, we can sure give an illegal access exception. Just wanted to show you a few of these. How do we want to handle this first one? It's not quite the same. What should we have here? And it's not going to be an index out of bounds exception. I guess this is a, let's give it a null pointer. This is the case, we should go back to our interface and make sure that we also throw a So if we're gonna throw a null pointer exception, it makes sense that we're checking whether element is null. And obviously the string, error string that we give them should say something like. All right, that makes much more sense. And now this red squiggly will go away as soon as we return something true or false. We always see this in not fully implemented methods. That was the case for our remove up here until we made sure that every path through this returned something. So this was red squiggled and now it is not, because we returned the associated things. This will go away when we return true or false.
We want it to be public, or it's.
The default is public, but we do want it to be public. Always better to specify the access modifier for clarity. Who wants to walk me through the logic? What do we want to do? Yeah.
Like first we wanna find a element in the list that we're looking for.
Yeah, we want to make sure we go through the list and find it. Are we guaranteed to find it? No, so we need to think about what happens if we don't find it. What are our termination conditions for that? So this sounds like it's probably a loop. We want to start at the head, check the head's data. And continue. So we could do something like say, we probably only want to do this if the list isn't empty. So let's make a base case here where if size is 0, then we want to return false. We were unable to remove something. To get past this if statement, we know that the size wasn't 0. So we're able to start the actual iteration process. So we can say something like. Yeah, assume that this is a primitive. So we need to use dot equals here rather than equals equals. Are we familiar with the difference between equals equals and dot equals from past classes? Yeah, yeah, so it's, if you are familiar with the difference from between shallow copy and deep copy, we talked about this in 212 yesterday, we can talk about it here as well for those who aren't in that, but. That's a good point. Question on Zoom asked the difference between the list being empty and the size being 0. There's no difference. You could use either one here. There is empty and size. I've used is empty before, haven't I? So why don't we do that? Consistency is a good thing. Excellent catch. So yeah, equals equals checks for, are they exactly the same object? So you can think of, if I go to a cloning facility and clone myself, then equals equals wouldn't apply between the two clones because they're me and the clone, because we're not the same person. Even though we share absolutely everything in common down to our DNA, we're not exactly the same human. So because of this, we need to use dot equals. Dot equals is going to compare field by field and check for the equivalence of the values of each of the fields, rather than are these exactly the same object. So element here is going to be different from this query. When we say that query is equal to the head and we move and we set query equal to something, then it's going to be checking and moving and being a secondary reference to the same thing. So just to be absolutely sure that we hit this, we want to say dot equals. And this helps for objects that override dot equals as well, because we don't necessarily know how that exactly is going to be done. So any object that you pass into this as element is going to have an overridden dot equals to know how we compare two objects to make sure that they're the same. So this just makes sure that it will work. And we've seen this negation before, Boolean before. You know, this just means not. So query.data.equals element would be true if they are the same. And now this is going to be true if they are not the same, because we want to continue going through the list as long as they are not the same. As soon as they are the same, we've hit our target. We know what we want to remove.
Can you just eliminate line 101? And that second is empty loop. It really doesn't. do anything.
Yeah, I guess we
Other than
could
the
throw
return
new illegal access argument, because yeah, I don't, we would be throwing the argument here if it is empty anyway.
We can incorporate the return statement into. To the early.
It would throw the, throwing an exception ends the method anyway, so even if we had put a return after, it would never reach it. So yeah, no, you're absolutely right, this entire if statement is useless, because we already checked it is empty and it would never actually trigger this. So you're right, it is something that we should consider if there's nothing in the list, but we already hit it with one of our preconditionals here. Also a good catch. All right, what do we want to do inside of this while loop? Yeah, we got to make sure that we modify query. How are we going to do that? Beautiful. So this just makes sure that we're moving to the next node, then the next node, then the next node, until this while statement is true. I know that it's a negated statement, so we're looking for something that is the same between element and query. As soon as they have the same values at a deep copy level, then we're ready to make sure that we remove that. What do we need to do this? How do we actually remove that? Yeah,
We need to keep track of the node before it, so we can kind of loop over it.
you could keep track of it as you go and keep track of it and update it as you go. You could call it once at the end. Is there going to be one that is more efficient than the other? We definitely need access to that previous node to be able to connect it. There are two different ways we could do that. Does anyone have a preference as to how we do it? Do it after? So we could say node T pre equals find node before. But that requires an index, doesn't it? Find node before takes an index. We don't know what the index is, we know the node. So we would need to write a separate find node before that takes a node and looks for that. So I actually think it might even make more sense to do this as we go.
Well, you could just store like an index and iterate it and then -1.
Yeah, we could store the index as we go. That's probably a little bit less clean. But also, we don't want to bump up the other one the next time, so maybe that is the. All right, so now we should have the previous node and the current node. So now we're able to do exactly what we did before. We've set this up nicely to be ready. So we can just say that Previous next is previous next, like we did before. So I think we basically just copy both of these lines. And return true. We were successful.
But would it actually be better to store previous because like you're looping through the whole thing twice now?
You are, but every time you move up, so if you think about it. Let's say this is at the query node is at the position 5. How much work is it to find 5, 1, 2, 3, 4, 5, and then find previous if we're keeping track of it as we go? When we make this step, this second step right here, we're gonna be doing this. When we do this, we're gonna be doing this. When we do this, we're gonna be doing this. When we do this, we're gonna be doing this. So we're kind of doing that loop step by step every time we're going through this loop, if we do it that way anyway. Versus if we wait till the very end to find before, we don't do any of this work and then we do it all at the end. It's just a matter of do we do them at the same time or do we do this secondary work all at the end?
That'd be an efficiency issue.
It's exactly the same efficiency. That's what I would argue, is that we're gonna be doing exactly the same amount of work regardless of which way we do this. But one other thing we're gonna talk about when we get to efficiency is that we actually really only care about the mathematical order of efficiency. And so even if we end up doing twice as much work, that's not gonna bring us into a new order. So it's not a hugely consequential decision. Obviously, you want to make things bleeding edge efficiency if you can, and it's still worth thinking about, but it won't actually change the big picture running time of the algorithm, or how it scales as we get a bigger and bigger and bigger list. It will always be twice as much work, as opposed to as the list gets really, really, really long, it can start being factors bigger. So that's what we're going to talk about when we get into efficiency. It's one of my favorite topics in this class, because you really get a sense of mapping algorithms to mathematical functions, and you get to draw on some of your prior mathematical knowledge in ways that you can start visualizing algorithms as graphs, or as you're plotting the algorithm's running time and complexity on a mathematical function, which is cool. It's really cool. Questions on this remove? Anyone see any issues? This shouldn't be an index out of bounds. This should be a null pointer. Great catch. All right, one other thing we might care to do is to be able to change the data at one place, at one node with another piece of data. So we're going to call this update. Let's go grab update. So we're passing in an element that we're going to be updating it. We can do this exact same check for the null pointer exception. The index out of bounds exception is the same as our old index related index out of bounds exception. So we should grab both of these. This really makes me want to have a separate method for error checking. This just screams ugly to me. All right, so now we've made sure that we've met our preconditions. By passing all of these if statements, we know that the list is not empty, the index passed is not out of bounds, and the element passed is not null. So we have an actual element to go replace some element at a particular index with that. Great. How do we do it? Maybe before we even think of that, are there any special cases that we should consider?
I'll check if index is 0.
Yeah. If we're trying to look for the head, then maybe we can handle that separately. Maybe not, we'll at least go do it and see if we can combine this with something else eventually. If the index is 0, we want to do this to the head. So we want to change what is currently stored in heads data to be the element that's passed in to the update function. So head dot data gets element. Since this returns a Boolean, we successfully were able to do this, so we should return true. Any other special cases we want to consider? We actually aren't making a new node, we're replacing an existing node with a new value, so I think the size should stay the same.
Can you just do else? We're never trying to like access the thing after the last one or anything.
Sure. So how are we actually going to go do this? So we need to, this is searching for the associated index. Do we feel like we've done this before? Where did we do very similar logic? So yeah, we have the associated index here. We want to just search for that and grab the node for that. So we could reuse find node before. Sure. Now, since we want to update the value of the new node, how do we do that?
We have to change pre.next data to element. I guess pre.next data gets element.
I like it. Is there any way, whenever we see this next dot data, is there any way that this could be dereferencing null? If we're at the tail of linked list, yes. So how do we want to deal with that? Where should this be stored if this is the case? Well, what do we want to do to do this? Oh, we have current. We do have current, yeah. So what would that look like? Current dot data. And that also bypasses the entire loop here. It's all, even if this was just extra code that wasn't necessary, this would mean that we don't have to go through the loop that's embedded within find node before. And it would save us just a little bit of time. Probably not a relevant amount of time, but it is slightly better efficiency, ever so slightly.
Are we supposed to be like incrementing current through some of the other methods?
Yeah. Yeah, we'll figure out exactly how that's how that's botched as we test this. Because I think there's some good outcomes from going and testing, seeing something that doesn't work quite like it should, and then going back and looking at our code to figure out what that should be.
We need to update our index out of bounds exception on 116 to be index greater than size minus 1. Here,
Yeah, it should be. They should always be greater than or equal to size, shouldn't it?
greater than.
Here, we should also return true. We're successful. I think we're good there. Anyone see anything else that needs to be done? Oh yeah, we need to return. We're here, right? Yep. Now the squiggly goes away. Should have been an alert. Great. We can write our really easy methods now because we need to make sure that we implement size and let's see, size returns and int the size of the and then we need is empty. Is empty is true or false. All right, maybe we're ready to test. Do we feel like this might be complete? What's left? This has gone away, which means we've implemented everything in the interface. So we could at least test. So why not? We'll see if this works. I like to call my mains not just main, but a driver and a particular kind of driver. So this is going to be a linked list driver class that's going to kind of work with and be some basic tests. We're not going over unit tests in here, so I'm not going to write them as unit tests. I'll do this more in 212 than 300. So in this case, we want to make a linked list. So we can say what did our linked list constructor take? Anything? No. So this makes the list. So we're ready to start doing things. Someone tell me something we can try out and see if it works. I'm gonna start with something that I think should throw an exception. With this. Remove 0. Trying to use the job as linked list. This is a problem. We did a generic, didn't we? That's the issue. You'd still be able to attempt to do this, though.
You gotta implement your linked list.
Yeah. No, we shouldn't need to. What else can we do to test this? What's? Seeing an issue with remove? No. I'll figure this out eventually.
Oh, you would just put it in a public site void main.
Duh. I love it. I love it so much. I'm a dumb. We all make these mistakes. Doesn't matter how much experience you have, you still make the basic mistakes. So this should give us the exception that we expect. Why are there errors? Figure the project to correct. Well, I'll do this before our next class. What I want to start thinking about is iterators. I won't waste more of people's time. So. Does.
Yeah, it works. I got them.
Yeah, this is an Eclipse specific. It's not locating the files quite correctly. It should work in IntelliJ. So what we're gonna do is we transition, we're gonna start talking about iterators. And iterators are a way for us to be able to do things like in the middle of a for each loop, we want to make changes to the list. Has anyone ever tried to do this before? It ends up being an absolute nightmare. Imagine that you make a list like this, and then you say, you add a few things, and then eventually you say for integer I in your list. You want to do something, and this obviously isn't gonna work until I get this to work, but let's say in the middle of this, I want to say like if the element is 5, then remove it. In the middle of this for each loop, you're gonna get a kind of exception that you've never seen before, and that is a concurrent modification exception. So if we want to be able to do things like iterate a collection like this and make changes to it, add to it while we're iterating, remove from it while we're iterating, then we need a special kind of structure called an iterator to be able to do this, and some additional logic that we need for it. So I'm going to talk about that, as well as we're going to implement an iterator into this linked list. So I will see you tomorrow for that. Have a good rest of your day.